Thank you for the introduction. And can I just confirm that you can hear me and see my slides?
Yes, we can hear you.
Great. Hello, and so yes, I'll be talking about Power Models Restoration, this Julia package framework for power network restoration algorithms. So the starting point here is going to be, what is grid restoration? What do we mean by this sort of grid restoration algorithms? What we're looking at are severe contingency restoration problems, where the problem is that there's a significant portion of the electric grid that is physically damaged and needs to be repaired. The objective here is to order those repairs to minimize the amount of unserved energy in the system. So this is the total load that's not being served, as well as the amount of time that that power is not being delivered. As an example of that, you could think of a hurricane hitting the Gulf Coast of the United States. The hurricane comes across and it damages a portion of the grid here. These are perhaps substations that have been flooded, transmission lines that have been blown down, and we need to make decisions about in what order do we prioritize these repairs to happen. And now, what exactly makes these restoration problems so challenging to solve? There are two aspects that affect the difficulty of these problems. One is the power flow that is used to solve these problems. The reason being is that for every single repair that we're considering, there's a copy of the entire network variables. And those decisions represent which one of these devices has been repaired. So there's all these linked topologies that are linked by the previous repairs that have happened. So in a sense, every single repair that's considered is another copy of all the power flow variables. And that power flow itself is then going to be very deterministic in how difficult the problem is to solve. And then the other factor is the number of copies is those numbers of repairs that we're considering in the network. So these are these two factors, the power flow and the number of repairs being considered. So in a sense, there are two ways we can address the difficulty. We can use a simpler formulation of the power flow, and also we can start to address algorithmic heuristics to reduce the number of decisions being considered. The formulations can include linear, such as the DC power flow, or nonlinear convex relaxations, as well as the full nonlinear non-convex AC power flow equations. And then on the algorithmic side, by reducing the number of repairs being considered, there's both a reduction in the number of network copies, as well as the number of mixed integer variables in these optimization problems. On the formulation side, there are three that we consider. The first is a linear approximation of the DC power flow. This is going to be very fast, but it will make some assumptions about the network that may not hold up in a severe contingency situation like this. It's going to ignore reactive power in the network, and there may be reactive power devices we need to restore in order to have a feasible power flow in an AC solution, and this would not be considered. There are also assumptions about nominal voltage or small voltage or small angle differences between nodes, and again, these may not hold up in a severe contingency. As a nonlinear convex relaxation, we consider the second order cone power flow here. These will better account for reactive power flow than the DC problem, but it will be much slower to solve, and it is still a relaxation that may be AC infeasible in this severe contingency network. And finally, we have the full AC power flow equations. While these are going to be accurate to the physics, these are very difficult to even find feasible solutions with these restoration algorithms, and we can often get stuck in local optimal solutions even if we do find a feasible solution. On the algorithm side, I'm going to go into a bit more detail about what are some algorithms we're considering in this set. One of them is going to be a pre-processing step that we call the minimum restoration step problem. This is a pre-processing optimization problem that is going to find the minimum number of repairs that are needed to provide full power in the network. This is in order to reduce the number of decisions that we're considering when we're ordering these sequence of restorations. But I want to point out that this is going to be a heuristic. There may be certain combinations of repairs that do provide more energy to the network, but would require more repairs. And we'll see an example of this in the numerical results. What I will say is that this initial preprocessing step is a single time period problem. And when using this preprocessor, that solving both problems back to back is going to be much, much faster than just solving that original restoration ordering problem. Another consideration we can take a look at is restoration redispatch. Here, we can solve the restoration sequence with a linearization or relaxation, and then take that fixed topology and just redispatch all the generators in an AC power flow. The goal here is that we can get away with using a simpler formulation in the ordering portion of this step, but then be able to recover an AC feasible solution when we're actually using this restoration sequence in practice. But there is still potential for suboptimal repair ordering because we're not considering the full AC power flow equations and so on. However, perhaps we can address larger networks by using this redispatch. And then a key point is that we can actually combine these sequences together, where we can take that network data, we can first do this pre-processing step, find that minimum set of repairs that need to be done, order those repairs, and then ensure an AC feasible dispatch at the very end. And this can come across with different power flow formulations on every single one of those steps. What this really looks like is this trade-off between fidelity and tractability when solving these problems. While the AC power flow equations are going to be very high fidelity, they're very difficult to actually solve here. On the other hand, DC power flow may not be accurate enough to give a good solution to these problems. Perhaps there are some convex relaxations in between that could be a good trade-off here. On another side, we can perhaps recover a higher fidelity power flow using algorithms like this redispatch of the generation in the problem. But then there's also questions of like exactly how accurately do we need to order these repairs to have a good solution of considering every single damaged component in the network and ordering all of the repairs, or just selecting a subset of them and ordering that subset of repairs. In order to take a look at this, we developed a software package called PowerModels Restoration in the Juliet language. This is a software framework for designing and testing restoration algorithms. It has a mathematical modeling layer for the core restoration tasks, and this can include selecting the problem formulation, whether we're doing this pre-processing step MRSP or that restoration ordering problem, and then selecting a powerful formulation that we're going to use in that problem. And we can combine these formulations and heuristics together to create complex workflows to try and tackle larger networks. I will mention that there is some math behind all of this problem, but I don't have time to get into all of the different formulations for these different power flows and problems in this 15-minute presentation, but I'm happy to take questions on it at the end, on exactly how do we model some of these restoration portions of these problems. On the numerical results, first I'll be taking a look at comparing the different power flow formulations while repairing all of the different devices in the network, that full restoration ordering problem. Here, we're taking a look at the 5-bus network you can see on the left-hand side, and the initial network here is assuming that every single device in this network has been damaged, and we need to fully recover the network. The graph on the right shows the amount of unserved energy on the y-axis, so the amount of power and energy that's not being delivered in the system, and then across the x-axis is how many repairs have been done cumulatively. In the orange here is the DC restoration ordering problem. You can see that at the beginning, there's quite a bit of energy that's not being delivered in the network. And as repairs happen, that number is going down. And after 7 repairs, all of the power in this network is being delivered to the loads. The second order cone formulation actually has the exact same solution. That's not always going to be expected, but with such a small network, it's not unusual that this might happen here. In comparison with the AC power flow, there's actually more unserved energy in this problem. And you can see that it also requires 8 repairs to be done before it can fully power the load in the system, unlike the first 2 examples where only 7 repairs were required. The problem here is that AC formulation actually found a locally optimal solution. And if we can go back and verify the DC and second order cone formulations, we actually find that those restoration sequences were AC feasible. In a sense, using the most accurate power flow was not able to find the best solution to this problem. In addition to the fact that AC power flow was much more difficult, took much more time to solve. Next, we can take a look at that minimum restoration set problem, that pre-processing step with the second order cone power flow formulation. Here we're looking at that same 5-bus network, but now on the left-hand side, you can see the components that were selected by that pre-processing step as a minimum number of repairs needed in order to fully power the network. The graph on the right in the orange is the same solution that we saw 2 slides ago, just that regular restoration ordering problem. And then in the blue is that pre-processing step followed by that restoration ordering problem. What you can see here in the blue at that 6th restoration period is that it only took 6 repairs to fully power the network. But there was more total unserved energy. The issue here is that certain combinations of repairs, when considering all of them at once, could have less unserved energy in this problem. But doing that, considering all those repairs together, is much more difficult to do. There's more mixed integers in this problem, mixed integer variables in this problem. It's a much more challenging problem to solve. And finally, we're going to take a look at that redispatch of the generation in order to try and recover a higher quality power flow solution to a problem. Here we're taking a look at the 118 bus network, where about 10% of the transmission lines have been damaged. In the blue is the restoration ordering problem with that DC power flow. According to the DC power flow, only 4 repairs are needed to fully power the load in the network again. When we take that solution and then redispatch generators on an AC power flow, there's actually considerably more unserved energy, as well as more repairs needed to fully power the network. What's happening here is that the DC power flow is overestimating how much power can be transferred across the network to the loads when there's so many damaged transmission lines. In addition, it cannot correctly order devices after its objective function is maximized, all the power is delivered in the network, so that extra repair that was needed isn't necessarily going to be the next one that was done. It could have been that next repair was several repairs down, and then there's this trade-off of, while we are able to even solve this with a DC formulation, unlike with an AC formulation, it's not clear that this will give a very good solution all the time. And this redispatch will ensure feasibility, but it's not an assurance of a good solution every time. In summary, what we're looking at here is this trade-off of fidelity and tractability. Perhaps we can use lower quality power flow formulations, but we don't get guarantees on a feasible problem. On the other hand, we can use a really high quality solution, but maybe never even be able to solve it. With that AC power flow, like I mentioned, it's hard to even find feasible solutions to these large restoration problems. There's some relaxations, like the second order cone relaxation, that might give some good restoration sequences as a good trade-off of fidelity and tractability here. Using a DC power flow for the restoration sequence and then an AC power flow on the redispatch may be a way to consider larger networks, but there are some considerations that have to be done in order to use these solutions. In addition, we can take a look at some heuristics that will reduce the number of repair decisions as a method to also be able to address larger networks that need to be solved here. And the code for this project is available on GitHub at the link at the bottom of the slide. Thank you.
Thank you, Noah, for keeping the time. Here we have 3 questions. The first one is how the single period optimization in the pre-process stage ensure the existence of a feasible solution at the end.
Yes, there are some considerations that have to be done there. For example, in some cases, we do have to have a soft lower bound on voltage in order to achieve that, but that existence and our assumption on being able to shed load does guarantee that there is a solution at the end by having with that pre-processing step.
Okay, thank you. The second question is from Ho Young He. How to consider the ramping rate of different generators? How to consider the patches to crank generators?
Yeah, so a part of this is also maybe how long does each one of these restoration tasks take? Is a restoration task something that takes a week to do, or is it a few minutes? So in this formulation, we do not consider the ramp constraints, but that is something that would be very good to incorporate if we also have very good data on exactly how long one of these repairs may take. But here, we're not looking at those ramping rates because it's not even clear that those time constants are going to be relevant to this problem.
Thank you. The third question is from Kit Bell. My understanding is that one of the main challenges in a real system restoration process is the management of voltage, energizing sections of the network and then managing steady-state voltages on a lightly loaded network. That suggests a need for an AC load flow to assess the system state for possible actions, or at least a very good convexified one. What's your experience of voltage issues in system restoration?
Yeah, that's a very real problem with this. The sort of approach that we are looking at here is more about what is a good topology that will lend itself to providing more load in the system. And then once we have that sort of fixed topology, then we can start to examine how do we adjust operation of the network to make sure that those voltage issues aren't going to be too harsh. So that it's again, the sort of a trade-off of we can't maybe consider all of these restoration ordering sequences with that full AC power flow formulation. It's just completely intractable. Can't even solve, for example, I haven't even solved any system larger than that 5-bus system that's been severely damaged in less than a week. So it is sort of this trade-off of what's a good topology to be able to solve here versus that sort of online, what are the dynamics of the system?
Okay, thank you. We have still a few minutes to answer the last question. In the redispatch stage, it's assumed that the sequences are fixed.
Yes, the sequences are fixed. All the mixed integer variables are sort of fixed in the problem. So all those networks can then be redispatched independently of each other and verified that they are feasible.
Okay. Thank you.